Okay, now let's go to the third principle, Muller-Breslau principle. So it says this: inference line for any action in a structure is equal to the deflection curve when we remove the action and replace it with a corresponding unit displacement or rotations. All right, so yeah, it's stated in English, but it's hard to comprehend. It's hard to understand what it means. So simply put it, inference line is equal to properly disturbed shape of the structure. So simply put it, the Muller-Breslau principle is inference line is equal to properly disturbed shape of the structure. Okay, so how can that be? You know, we are going from a bunch of equilibrium calculation and say that now all we need to do is to disturb or to deflect the structure properly. Then that shape will be the inference line. All right, so to understand that, you actually have to look at so-called virtual work principle, which is coming next. So before that, let me just illustrate this to you. So what is the inference line for AY? Reaction force at A. I want to find the inference line for this reactions, AY. So what I can do, look at the inference line AY. We can obtain this from point-by-point calculations or just simply doing one calculation inference line. Then we can construct this inference line. So this inference line, you can imagine that all I need to do is just properly move this point upward with a unit of 1 while constraining this point. Right? It's just like rotating with this point fixed, rotating the structures with units of 1. So if you draw this kind of deflection shape, then this is the inference line. So if you can just deflect it properly, then the inference line comes out. Remember that for determinate structures, inference line should be linear segments, straight line segments. So you just deflect that in a rigid body fashion, then that will be your inference line. Okay, so how do I comprehend that? How do I understand that? How come it is so? So we have to look for the answer, look for the explanation from this principle called virtual work principle. So in this course, we'll be discussing a lot of virtual work principles or energy principles because they are one level higher principles that you can use after the equilibriums. All right? Equilibrium is always the level 1 principles. And one level higher will be the energy principle, the virtual work principle. Okay, so let's look at what is virtual work principle now. So I'm discussing a special case for virtual work principle. It's called virtual work principle for rigid body system. Now, whether you get this point or get this chapter or not depends on this, all right? Be careful. So we're discussing only one special case for virtual work principle. It's called virtual work principle for a rigid body system. So rigid body means that the system is not deflecting, no curvature. Whole thing is just a rigid body, all right? No curvature. So if you move, the whole thing has to move as a rigid body, okay? So let's say that I have such a rigid body, and it is acted on by some forces. And I say that this rigid body under force action is in equilibrium. So with that, I mean that the summation forces acting on this rigid body has to be equal to 0. So that's very obvious. If this is in equilibrium in the space, in the universe, then all the forces acting on it has to be summed up equal to 0, right? Otherwise, it will be moving. All right, so that's called equilibrium. No problem. Now, imagine now I can create some small disturbances to the system. I can deflect the system any way I want. But this kind of deflection, this kind of movement has to be very, very small, infinitely small. It's called virtual deformations or virtual displacement. So imagine I create a very small deformation or small disturbances to the structures, so small that it's not affecting the equilibrium conditions. So the work done due to the presence of this virtual deformation or virtual displacement is going to be equal to 0. I have one person going from that door to the other door. Anyway. So this kind of virtual deformations is going to occur at the locations of the loading as well. So this virtual deformations, this is for the whole system, is going to be casting some sort of virtual deformation for forces F1, F2, F3, and F4. So each one of them will be associated with kind of virtual deformation, right? So this are virtual, means imaginary, not real, right? It can defy, it can go against the support condition, go against any physical logic we might have. All right, so the work done by the force due to the presence of virtual deformations is very simple. Force time deformations. Force time deformation is the work. So total force is this, and this is the virtual deformations for this system. So it should be equal to 0 because the force itself, summation force, is equal to 0. We are talking about very, very small, very minute, very small deformation. So small, it's imaginary. Okay, so this work can also be formulated force by force. So it can do it like that. So it can go to each one of the force and then multiply its corresponding virtual deformations and then do a summation. So it tells you that the work created by this virtual deformations, when you sum them up, is equal to 0. The reason for that is the structure or the system is in equilibrium. So summation force is equal to 0. So any disturbances, infinitely small disturbances that you put in will not throw in additional work. So virtual work should be equal to 0. Okay, so this is a so-called virtual work principle for a rigid body system. So next, I'm going to use this principle to illustrate that we can actually bypass equilibrium calculations. Just use this work concept and then come up with an inference line. Okay? So bear this in mind. Delta W equal to 0. So let's go. So I'm going to illustrate how I can use this concept to construct inference line now. So Muller-Breslau principle say that inference line is equal to a properly disturbed shape of the structure. So I have A and B. This is a structure. This is the downward unit force. And I'm trying to construct the inference line for AY. So I disturb the structure. I disturb the structure in this way. And then calculate the virtual work. And by the virtual work principle for rigid body motion, a rigid body system, the virtual work created under such a deformation should be equal to 0. This is virtual deformations. This is infinitely small. Infinitely small. Okay, so I say that I want to disturb point A by 1 unit. 1 unit. And then calculate the virtual work. So the deformed shapes, 1 unit there, create a profile. I describe this profile as fx. X means the locations of that point. So this profile is described as a function of fx. All right, so with that, then I'm ready to formulate my virtual work. So virtual work is simply equal to that. We say that this is in equilibrium, so if I create a small disturbance to the structures, the virtual work is going to be equal to 0. Now, what is the virtual work? Virtual work is simply just force time deformations. So force time deformations and force time deformations. So this is in the same direction, so it's positive work. This is in the negative direction, so it's negative work. So this is positive work, this is negative work. And according to virtual work principle, should be equal to 0. So move this to the other side. It tells you that AY equal to Fx. So what is AY? AY is a reaction force. So it tells you that reaction force is equal to this profile. So this profile is due to that you're pushing point A upward by 1 unit. So that profile is equal to AY. So what is Fx? Fx indicating this profile as a function of x. What is x? X is the locations of the downward unit force. So conclusions. This profile, Fx, equal to AY, and AY is the reaction that we're looking for to construct inference line. So conclusions. This is the inference line for AY. All right, so you see that no equilibrium calculations. All you need to do is just push point A up by 1 unit. That's it. This becomes the inference line for AY. All right, similarly, we can do BY inference line. Let's do BY inference line. So push B up by 1 unit while holding point A stationary. So do it like that. Push B up by 1 unit and creating this profile. Okay? Push B by 1 unit, creating that profile. This profile is Fx. So if you know this is 1, then you know what Fx should be, right? And then you follow virtual work principle. Because A is hold stationary, not moving, so there's no work done by AY. There will be work done by this downward unit force, negative work. There will be work done by BY, positive work. Sum up, virtual work principle says that it should be equal to 0. So BY equal to Fx. What is Fx? Fx is just the profile after you pushing B point up by 1. Okay, so it's quite intelligent. Depends on what you want. You just push that point up by 1 while restraining the other points from moving. All right? So looks okay, looks simple. So if you want to get AY, you just push this point up while holding B down, not moving. If you want to get BY inference line, just push this point up while holding A, not moving. Okay, so far so good. So that seems easy. That seems easy. Again, no equilibrium calculation whatsoever, right? All right, next, tricky point. This is tricky now. I want to find shear force there now. What is the inference line for shear force at this particular location? So I need to properly disturb the structures and using the delta W equal to 0, virtual work principle equal to 0. Okay? So how do I properly disturb the structure? So here, I properly disturb the structures like that. You see why. You know, there's always one unique answer. You know, there's no other answer. So this is the properly disturbed shape. You know, you cannot randomly disturb shape. This is properly disturbed shape. So what is that? Let's see whether the delta W will tell us the answer. So let's say I cut it open there and rotate the left-hand side clockwise, and then rotate the right-hand side counterclockwise. Clockwise. This is clockwise, this is clockwise. Both of them clockwise. All right. So rotate this clockwise, also rotate this clockwise. So shear force on this cross-sections, right-hand side of the cross-sections, is defined as positive and positive like that. On the left-hand side of the cross-section there, is defined as positive there and positive there. Okay? They are all defined as positive. All right. So properly deformed shape, you need to tell me what is this deformed value and what is that deformed value. So you need to know what is delta 1 and what is delta 2. So if you know delta 1, then you will know this rotation angle as well, theta 1. Remember, we are talking about very small deformations. So delta 1 and theta 1, they are related through delta 1 over this length is equal to theta 1. So same thing. Theta 2 can be related to delta 2. Simply just delta 2 over this length equal to theta 2. Okay, so with that configurations put down, now I can formulate my virtual work. So here is a virtual work. So just look at the force one by one. So this force, shear force, is going to do work because this cross-section has been pushed down with this deformations, delta 1. So this shear force is going to do work. It's V times delta 1. So V times delta 1. Same thing. This shear force is going to do work because this cross-section is being pushed up delta 2. So they are in the same direction. So V times delta 2. So here, V times delta 2. Bending moment, M, is going to do work. This moment is going to do work because you have a rotation angle there. But they are in the opposite directions. So it's going to do negative work. So M, theta 1, but minus here. This moment is going to do work because it has rotations. So M times theta 2, same direction. So it's positive work. So here. Okay, one more force that do work is this external force. So external force together with this profile is going to do this work. Now, I'm looking for inference line for shear force. So you can imagine, I want to say V equal to Fx. So I want to say V is equal to Fx so that this Fx become my profile, become my inference line. So how do I make V equal to Fx? Well, two conditions that you need to satisfy. The first one is you need to make delta 1 plus delta 2 equal to 1. And the second thing is you need to make theta 1 equal to theta 2. So by theta 1 equal to theta 2, then this bracket there is equal to 0, so this term will be out. If delta 1 plus delta 2 equal to 1, then is V times 1 equal to Fx. Perfect. So these are the two conditions that can help you to finalize the shape, the precise shapes of your inference line. So first you let delta 1 plus delta 2 equal to 1. And secondly, you let theta 2 minus theta 1 equal to 0. So with these conditions, then you can construct this profile precisely. So the result is V equal to Fx. So Fx is the profile. So we are done. The profile will be the inference line for shear force, as long as this profile satisfies this and that conditions. Okay, again, no equilibrium calculations. All you need to do is to ensure that the shapes that you created satisfy these two conditions. All right? Is there any questions about this?
Do we have direction for the delta 1 and 2?
Yes, we do. Yeah, we do. This is downward, this is upward.
So how
Yeah.
do you define the direction?
Direction.
Yeah, the
Especially for the
positive
moment
and
part, why the sigma 1 is minus?
yeah.
Come again?
Why you use minus and sigma 1 instead?
This?
Yeah.
Because this is clockwise. This is counterclockwise. Now, of course, if it turns out that it tells you that theta 1, theta 2, theta 1 has to be negative, then you just flip. So it depends on what you get out of it. Now, you'll be solving this profile under these two conditions. Right? Anyway, next, I'll show you how you can construct inference line for bending moments. I'll give you real examples after this. Okay, next I want to find inference line for bending moment now at that particular location. So I want to find a properly disturbed shape of the structures so that that disturbed shape become my inference line. That's the whole purpose of Muller-Breslau principle. Okay, so properly disturbed shape. So what is a properly disturbed shape for these conditions? So here, this is properly disturbed shape. So why this is properly disturbed shape? Let's see. Virtual principle will tell you. So imagine that I disturb a shape like that. Move this point up on both sides. And the profile created is called Fx. Okay, so when you open up a cross sections, you always see two pair of forces, shear force and bending moment, right? So shear force pair and bending moment pair. So you need to figure out what will be appearing in your virtual work calculations. So imagine that I pull this point up by delta. Then I will have a rotation angle theta 1 created because of that, and rotation angle created on the right-hand side as well, theta 2. So I can formulate my virtual work principle. So virtual principle is shear force, one side is downward, the other side is upward, but they are moving together with the same amount. So shear force will not do any virtual work. Bending moments. This side rotating counterclockwise. The moment is counterclockwise, so it will do positive work. This side's moment is clockwise, rotation is clockwise, so you will do positive work as well. So work done by the moment is that shear force is not doing any work. And you notice that point A, point B are hold stationary. Point A, point B. They won't get into your virtual work because they are hold stationary. Okay, so with that, the only thing I need to do is just make theta 1 plus theta 2 equal to 1. Then M is equal to Fx, right? If that is equal to 1, then that's it. This is what I want. M equal to profile. M equal to profile. So that's it. That's the only condition that you need to impose in order to get the inference line for bending moment at that particular location. Isn't that beautiful?